Hello friends, welcome you all to the last session of this ARM development course. So in this, what I plan to cover is a few more ARM processors. Okay, there are plenty of ARM processors. After having discussed on ARM7 TDMI in detail about the instructions and other features of a particular processor there, and then we talked about a lot on other memory management and cache and hamburgers. There are a lot many things we discussed. So I would like to conclude this lecture with a brief introduction to various processor cores that are available in the market and what their target applications for which these processors are being developed. And so this will give you some flavor of what all is there. The learning about ARM this cannot end with this. We can in fact go deeper into the recent architectures, the features, and the multiprocessor cores, which are very unique and very interesting to go deeper into, as well as lot of features which are DSP specific for Java support and there's a technology called big.little which I will talk about. So plenty of architectural innovation continue to be going on in the ARM family. So support of 64-bit processors, quite a lot. So having gone through this course and having understood all the major functionalities, now learning about the feature processors and the advanced features will be very interesting, and it will add on to your knowledge, and certainly the knowledge that you have gained through going through this course will be helpful to read up and understand future processors, as well as you can be in an architectural design team designing new processors. Okay, so my intent was to introduce you to the beauty of architecture, processor architectures, taking ARM as an example, because this is a very good example to take up to teach processor architectures, and with a lot of practice in assembly language programming, you can become an expert in assembly programming as well as in the processor architecture area. Okay, so let us go further. So you all of you are familiar with instruction set architecture, and then I will talk about a few instruction set architectures. What we saw so far was ARMv4. Now I am starting off with the 6, 5, 6, 7, and 8, ending with the 8. So there is a plenty still coming, and there is a lot of innovations happening in this area, and I am pretty sure that you will go deeper into the future areas and then contribute for new architectures and then developing solutions based on these architectures. Okay, so this I have already talked about, which I showed you in the early classes. So this is where we spent a lot of time initially on the instruction set. Take every instruction we went into detail of ARM7 TDMI, which is where ARMv4 T sorry. So let us talk, see what are the additional features which have come into it. So you can say that this is everything is actually inclusive of whatever there before. So it has got ARM thumb mode, okay, extra instructions we have added, and then enhanced multiplication instructions, and then DSP type instructions, and Java acceleration. Okay, as you all may be aware that Java runs on bytecode. Okay, Java is converted into Java bytecode and then runs on GVM. So ARM provides JSL support state where Java code can be run natively on the architecture. So with the architecture support, Java execution becomes faster. and then include multiprocessor instructions, and then even accessing unaligned data as well as mixed endian data handling. There's plenty which have come into this ARM 9 and 11 families which fall under this instruction set architecture. So the intent of this course is to just give you the list of features and what all is there. Maybe we don't have time to go in deeper into any of them, but this is an overview which will make you go into deeper, by looking at the different documentation. So, based on your interest and what you are looking for. Okay, so these are all different families, and these are the additional DSP and other instructions which are coming to different ISAs. We'll see them in detail. So this is a higher level view of how the instruction set architecture has evolved. So there is security is very important, especially in networking, and there is all the encryption and key generation, those kind of things which are required for network protocols. There's a lot of support from the ARM processor with a separate module for it, and then thumb2 is additional add-on to the thumb state, where not only 16-bit instructions get integrated in the thumb2 technology, even a few 32-bit instruction set also gets integrated, being in thumb state. So actually, the power of thumb2, the thumb state has been improved, has tremendously been improved in this introduction of this particular feature into ARM. And then we saw the better floating point processor, and it is been improved, as well as there's advanced SAMD architecture which has been built into the latest processors. And the V8 ISA has both 32 as well as 64-bit architectures. So I'll talk about this in the subsequent slides here. And crypto module is also added to it. So plenty of additional hardware and features gone into this. Then design is a Java support. So this is the overview of what are the features which have gone into the data processors. So let us start with ARMv5. Improve efficiency of ARM and thumb interval. That is how they work together. And then the new instructions. Just a few examples. Counting leading zero. So suppose you have bit pattern like this, and then 1 and then some zeros. So suppose if there are no 0, 1 after this. Now how many number of zeros here? Okay, that you can easily count using one instruction, which is the execution. Otherwise, we may have to do a rotation, okay, or shifting operation to find out how many are there. Okay, till we encounter a 1 which goes into the carry bit. This has to be shifted to the left, which will involve lots of cycles. So to avoid that, there are value shifter is there which will take only one cycle. But what happens is we may have to see whether carry flag is set or not, and then we have to find out. We have to keep track of how many zeros were there. So it can't be done with just a shift where we may lose the number of zeros that we counted. So that's why I'm saying that it will involve a lot of instructions. But whereas if you have the two registers and then you say that I pass one and bit pattern, on 32-bit value, and then I want the count in another register, so that will be easier to get, with a single cycle execution. So this kind of features which have been added, and then breakpoint is another instruction, which is actually when you are debugging inside the assembly, you can put an instruction called breakpoint. So what happens is the execution stops, and then there is a debug unit inside the ARM architecture. Okay, inside the SOC there is a debugger. For debugger, as I mentioned, some hardware is very integrated, emulating, and then some debugging capabilities are built into the hardware. So when it encounters the breakpoint instruction, then the control is passed on to the debugger. So the execution stops, and then later on what happens is this will be replaced with another actual instruction. So based on the breakpoint that you set in the debugger, that particular instruction is replaced with the breakpoint instruction in the assembly, and then when it reaches there, it will come to the next level. Suppose if you are doing a step every instruction in the assembly, then this will be possibly put into the instruction which is getting executed, so that processor gets stopped as soon as you can encounter. So these kind of features are very important for debugging purpose. And then introduction of E variant. This is the DSP processing algorithms. For DSP algorithms, there are instructions have been added in the E variant. So if you see E extension to the ARM number, then it is actually a DSP features are added to it. Some instructions which will help you in implementing DSP algorithm. Not that it is implemented algorithm, but some instructions which help you in developing DSP algorithms using ARM processor. So a J variant is for Java. General architecture extension is there. So bytecode execution is done there. So that is all about V5 from 7 TVMI. Okay, these are the enhancements in the next ISA which came up. So DSP has come, Java support has come, and then few instructions and then interworking of this has been improved. Now V6, the next instruction set are there. Here what happens, new instructions for into exception handling. So exception handling has become simpler with the additional instructions. And then exclusive access instructions. So this will involve some monitor and then multi-core processors, where you have variables which are to be accessed with the concurrency of other processors. Okay, so it should be exclusive access has to be done where the process, particular variable is shared between two processors. So it is useful in the multi-processing system, and this exclusive access instructions help you in achieving that. So hardware support is there. A set of single instructions assigned the media instructions. As there is a lot of media instructions have been implemented and supported in the processor. And additional function null instruction with accumulation into a 64-bit. So some more multiplication instructions have been added, and both virtual and physical memory system have been devised. And then a new, we saw ARM and thumb state, but thumb 2 technology is a little improvement on that from V6T2 versions. So what exactly this does is you can have both thumb state 16-bit instructions as well as a few 32-bit instructions too, okay, in the thumb state. So what happens is here the format is different. Okay, you may wonder what is the another 32-bit instruction that ARM supports. So ARM instruction, if you remember, there was always a 4-bit value which is conditional flag. It was most of the instructions default have this conditional flag. So in the thumb 2 technology, some of the 32-bit instructions which have been introduced in some state do not have this option. So it is used for some other purpose. The encoding can be used for some other purpose, and then the conditional execution is started given by another instruction, if condition. So that instruction has been added. So there are lots of improvement like this. And come to the major enhancement of 16-bit instruction. It adds 32-bit instructions, mostly unconditional, that can be freely intermixed with the 16-bit instructions. So in the original ARM7, when we were in some state, we were restricted with a few. We have to operate only with a few 16-bit instructions. We didn't have the flexibility of using 32-bit instructions in some state, but that restriction has been removed from after introduction of some new technology. Similarly, I gave a small introduction about tightly coupled memory in the previous lecture. So that support has been given from ARMv6. New hardware support for word and half-word unaligned access. So if you recall ARM7 TDMI, the word accesses are to be 4-byte aligned. Half-word accesses have to be 2-byte aligned. So there is no question of reading it half-word which is not 2-byte aligned. Okay. So that restriction has been removed. Okay, so you can even if it is not aligned, even an odd boundary will be made for involved. So that kind of flexibility is there. Formalized adoption of debug architecture. So coprocessor 14 is reserved for a debug architecture, and it has been formally included into the architecture definition. And high vector extension. So far we have seen that interpreter table has to be at a zero address, right? The IVT interpreter table needs to be at 0. So some cases where this memory cannot be given for initializing the vector table, some systems you will have an issue because of this restriction, right? It can't be anywhere else. So this location is reserved for that purpose. So the vector extension has been given, and then it has become mandatory from this the V6. So another address, higher address also is given for that purpose. So that helps you in terms of deciding where the interpreter table can be. And then ARMv6 requires that base restored apart model is used. Earlier it can be only base updated apart model. So if you recall, if suppose we were doing the LDM or STM instruction, okay, which has got a base register of course, and then it was copying either from memory to multiple copies, from memory to registers or registers to memory. During the time if there is an abort, then if you recall I mentioned that in ARM7 it will update the base register as if this instruction has been successfully executed. Okay, so you will always see that updated abort model only when it comes to abort exception, this base register will have been updated. But from ARMv6 there is a support for restored abort model. That means when it comes to execute exception, it would have been restored as if nothing has happened. So if it is restored, it is easier for after the exception to restart the instruction because you don't see that the base register is changed when you enter the exception handler. Whereas in the previous case, it is updated. So the exception handler has to deduce from the instruction how many registers were there in the register list and then how many would have been updated to, and then go back the base register value to the original and then start the instruction. So it was little involved in terms of writing a lot of code in the exception handling. So now that has been removed. So we can choose one of these models, and mostly we may prefer this because we want to restart the instruction most of the time and the data what happens. So that's all about V6. Then talking about V7, the next advanced ISA of ARM is a optional floating point extension. So that has come in enhanced exception and memory model. So both exception and memory models have been enhanced. So I'm not going into detail because it is pretty involved. So we don't have time bandwidth for covering all of them. So our focus was to learn everything about 70DMA which you have done. Now I'm just giving you in a nutshell what all has happened after that. So it's interesting to know. No, we shouldn't think that ARM7 DMA is the best architecture there, but there is a better architecture than that is there from ARM family. So it is better to be aware of that. So debug architecture that provides software access to debug features. So there is a lot of breakpoint and other features that are there that can be accessed through software, lot of debugging of features. And optional SAMD and security extensions. As I told you, encryption and other things could be implemented in this. It is also defined a virtual and protective memory system architecture, enhanced both memory models. Now, Cortex 8 series, okay, it's a family of application processors for complex OS and user applications. Okay, it follows this ARM's V7A. A means application processor and come to technology, which I have mentioned briefly about just now. So this, if you hear Cortex family, you should immediately remember that okay, this at least some of the Cortex A series follows 7A ESA. So that will help you to know what are the features are there in that particular series. So there are plenty of processor numbers A5, A7, MP4. So MP4 is a multi-core processor. So let me tell you what are the features in MP4. So Cortex A5, the smallest member of the Cortex A processor family. So please remember it is okay V7A. Let me write A here. So that is a instruction set architecture. High performance, low power with L1 cache. Okay. So this is the smallest member. Then A7 MP4. So large physical address extension, expanding the physical addressability and media processing extension as well as advanced performance. And then A8 provides full virtual memory capability. Okay, that is another advanced version of that. So this is how the complexity increases and the features get added. So the previous features are also supported, so that I am not mentioning them. Only additional things that also not all of them. I am just highlighting a few of the features which are there. So from A9, 8-bit Java bytecode in serial state was introduced, and then A15 MP4. Okay, that's little advanced compared to other cores. So you can imagine what we saw in 7TDMA was a 3-stage pipeline, right? Here 15-stage pipeline. Okay, and out of order superscalar execution. What I mean by out of order is the program assembly sequence will be in some way. Okay. Now, if the processor has multiple ALU, multiple maybe that null is there, add unit is there. Now, this superscalar, what does it do? Is it looks at all the instructions and then schedules them if there is an execution unit available and there is no dependency from the previous instruction. So in the typical 7TDMA, what we saw was all the instructions go in the same order in which it has been written. Whereas in superscalar, though as a programmer you have written this way, maybe this instruction can get executed before, okay, before this completes, because maybe this will be a null instruction and then this could be some just add or move instruction. But correctness is assured because in it is this instruction, the later instruction is not dependent on the previous instruction execution completely. So what really we gain is the processor keeps all the execution units and the processing units busy executing the instructions. Okay, it feeds dynamically allocates the schedules the instructions, so improving the performance. So that has been added in this. So these are advanced architectural features. And tightly coupled low latency L2 cache. Now you see that L2 cache also L1 cache was there previously, now L2 cache has come. And then because as it says it's a multi-core, one cores can be there together. So multiple processes we have not touched in this discussion, but that's very interesting and lots of research is going on in the multi-core processors and issues that are there in sharing data between them, how cache coherency is achieved. There's plenty of research and plenty of interesting stuff on multi-core processor architecture. And Cortex A15 running up to 2.5 GHz. So now you can imagine the speed, the clock rate of this kind of processor. And what are the applications it is useful for? Advanced smartphones, whatever latest smartphones you have, mostly you see that this is having an ARM core in it and especially a multi-core in it. Mobile computing, as well as high-end digital home entertainment and wireless infrastructure. So that's the great thing that the ARM is there in both the wireless infrastructure, that means BTS and then you see that a mobile is there. Okay, I'm drawing it like this, but no mobile is having an antenna like this, just to make you understand that this is a mobile. So the tower that you see with which the mobile talk to, even the tower has ARM-based processors in it. Okay? It will have its own network processor or other additional hardware added to that to enable the wireless protocols to run efficiently. But there are high-end ARM processors which are used in the wireless base station. And you see that a low power ARM processor are also there in the mobile equipment. So you can see the spread of the presence of ARM core in the networking domain. Okay. So the ARM A15 or after A15 could be used for this infrastructure also, and it is being used. Okay. And then low power servers. Now ARM cores are going into the server environment. So in the enterprise server environment, the powerful multi-core processors are going into it. So it's not only low power and used for only embedded systems. It is also ARM cores are used in servers and enterprise environment. So the wide variety of family of processors coming from ARM has enabled it to penetrate into different markets, not only restricting to its own embedded mobile or embedded tablet or embedded product. It gets into wide variety, okay, into the network, and both wireless and wireline networking infrastructure, as well as in the server environment. So this is something which you should be aware. If you tell that I have gone through ARM and I understand ARM, maybe then there will be some questions on this. So it's very interesting, innovative idea from ARM. So what it really does is it packs a high performance core, okay, like part of A15 multi-core processor with a power optimized companion core. So it is a two family, both are ARM processor, both are from ARM only, but this is A15, okay, and then there are two cores coexist in the same solution. Okay. Now, what is the advantage? Actually, when you are running a process, okay, um, the OS running there knows which core is A15 and which is A7, and then it can optimize the by choosing a right core for right process or application. So it could even move into this and then move it back into this based on what processing is involved. So you may wonder why is there a need for two processors. So this is a big. Okay, the big little means this is a big processor. That means very powerful in terms of performance and of course in terms of consuming power too. Okay, whereas A7 is a low end, it's not as high performance as A15 core, but it consumes less power. Now, if a solution has both a core in it and then an application based on the mode in it, so you might have heard about sleep mode and hibernate mode and so many things, right? So it's all done to save battery. So whenever there is no need for this high-end processor to be running, then the job is given to the low-end processor, and which will takes care of mundane tasks, and then which is not doesn't involve so much of performance. The task which is not performance critical is done in this low-end mode. So it's by keeping these two together in a solution, we get the advantage of low power at the same time performance of a high performing device. So it's a combination of both, and this is done using this core link. It's an fabric. I will show you some diagram that enables in sharing memory and then variable or whatever data between two multi-core processors and both big and little processors. Okay, fine. This pairing solves the contradictory challenges of increasing the performance while increasing the battery life. So that means by reducing the power consumption, by ensuring that the high right processor core is assigned to the right task. So the task which involves high performance core will be assigned to this A15 core, and then the task which involves a low end job will be done by the ARM A7. So if you try to do a low end job using this core, you will be wasting power. So this is a better optimization of this. So the core link cache coherent network offers scaling to 16%. You can imagine that even a 16 processor could be there in a single SoC. And this core link is a coherent network. This is also defined by ARM, and we can connect multiple cores using this. and it is very easy to implement also in terms of design. So time to market is good. So an optimal solution for enterprise applications, because you may need 16 processors kind of a powerful processor only when the enterprise application. So our server or network infrastructure, this processor core can be used. So this is the idea of big little. So keep in a single solution in a SOC have one bigger high performing core and then a low end core also, and then the software as well as the hardware running there, we can, with the support of hardware, of course, we will be able to allot a particular core for a particular kind of a process. Okay. Now moving on to ARMv8. Okay. Let us see what are the extensions, architectural extensions being introduced. So this I already told, Java acceleration as well as security, the zone is called the control, and these are all which I have already listed out. Now V8 architecture adds cryptographic extension to it. Apart from all this, which you have seen in V7, and this adds cryptographic extension. And then the extension basically enable ARM process to achieve a good balance between high performance and a low power and small code size and the frequency. So this is a very good compromise between these two and good balance between them. Now V8 profiles, there are multiple family of processors, and ARM architecture forms the basis for every ARM processor. Of course, over time the ARM architecture has evolved to include architectural features to meet growing demand, new functionalities, high performance, and needs of new emerging markets. So there are currently now two ARMv8 profiles. Okay, one is V8A, which is meant for enterprise, okay, or mobile high performance market, and then one is R, which is the real-time solutions which for embedded applications and automotive and industrial. So you can find out from the target uh, market it is aiming for. This is high performance device, okay, architecture with a maybe power consumption will be more, but high performance. Here, real-time embedded application, the responsive time will be very good, and power consumption is less. So, but it follows the same V8 architecture, ISA. Okay. So, what all is there in V8A? That is the application processor with a high-end or enterprise network processor. So, it supports 64-bit. Okay. So, what are the, but maintaining the same power efficient implementation. So in 64-bit, what happens is the addressing range becomes 64-bit. Okay. So far we saw that 32-bit addresses and which was 4 GB was the limit. Now 64-bit, gives you a wide range of address. Okay. So and it extends the performance also because 64-bit processors are there. Yeah, greater addressing range as well as cryptography instructions which have been introduced in the V8. And then 64-bit general purpose registers. So all are 64-bit, and as exclusive SPN PC. It is not part of general purpose register as we have seen in the previous architectures R13 and R15. So that restriction has been removed, and it has got a 64-bit data processing as well as extended visual addressing mode, and they have two kinds of execution states. Okay, that 64-bit execution state as well as 32-bit. So maybe you can have mix of both in the implementation, okay, based on the application requirement. And then let us see a few examples of ARMv8. This Cortex 53 is one you saw up to 15. Now Cortex 53 follows the ARMv8 architecture ISA. Power efficient processor capable of supporting 32-bit as well as 64-bit code seamlessly. Okay. Highly efficient 8-stage in-order pipeline. Okay, you saw out of order execution, super execution in the previous discussion, right? So here it's an in-order pipeline with 8 stages, so which is more than what we saw in ARM7. Suited for entry-level smartphones. Okay, and it can be a standalone application processor or paired with a A57. So 53 can be a low-end one, and 57 can be a high-end. So we can be parallel, paired following the big little technology that I have discussed. So 57, of course, it is a high-end processor with a multi-core processor. Okay, highest performance 64-bit processor. it has got out of order superscalar. So you can include this and 57 and 53 to form a big little configuration. Okay, and it has got a low latency level 2 cache also, and it actually this I have talked about coherent interface, host interface. So this ARMv5 and 4 is compatible with this particular processor. Okay, so an example of this, so multiple cores of 53 are there in this. Okay, and then this core link helps in connecting all these cores, multi-cores. Each of them is up to 4 cores per cluster. Each block what you see is a cluster which is got the code L2 cache in them. Of course, if L2 is there, L1 is inside. Okay, as well as multiple processor cores are there, and then these 8 coherent clusters can be interconnected using this cache coherent network with a shared memory, which is the uniform system memory. So they can share using this link. They can communicate over there. So it's the ARMv higher level, versions of ARMv specification here. And then there is a L3 cache also present in this. Okay, L3 cache. And then we see that the DDR3 and 4 which are double data rate external memory can be interfaced using this DDR3 and 4 interfaces, and then peripherals are on this bus. Okay, flash and then GPIO, all of these could be placed here, and then you can see that some other cores here. Okay, DSP core is here. Okay, yeah, DSP core is here, and then we have GPU. GPU is also Mali. There is a processor. You can just go through that. So graphic processor from ARM. Okay, and then other interfaces, SATA interface for the hard disk, and then PCIe for other peripherals. So plenty of things could be there in one place. Okay? This link helps you in terms of achieving this. Okay, this is a simple example of how complex the ARM-based solution could be with multiple cores in them and memory in them. So these are all used for network infrastructure or enterprise solutions or server applications. Okay, so ARMv8 RSA, there is a R series. I told you that this is a real-time series. So for that, Cortex R series is a family of embedded processor for real-time systems. So it has got a R4, which is a mid-range real-time processor. Okay, there are also multiple family of processors. So you see that R4F has got SPU support. R5 is for high performance. Okay, and then if you see F, it has got a SPU support. So embedded applications, you don't have to think that it may not need a floating point processor, because there may be a lot of requirement now for advanced processing in the real-time system. We need a floating point support. So there should be a processor architecture which is meant for real-time systems with low power capabilities, as well as has the capability of floating point processing in it. So we can choose based on the application whichever processor suits our needs. Cortex R7 NP core processor high performance multiprocessor for using vast range of deeply embedded applications. Okay, even there are lots of embedded applications where multi cores are used. Okay, so this is the right choice for designing such a solution. So with this, we have come to the end of this session as well as the end of this course. So here what I intended to do was to give you a higher level overview of various instruction set architecture, and then some of the features and latest technologies which are there in both for application domain as well as real time domain. So it has been a great journey, and I really appreciate your perseverance to learn on and having continued on this particular lecture. I really enjoyed sharing a lot of information about ARM, and I urge you to not stop with this. Actually, the intent of this course was to create interest in the minds of the people It's a natural interest. Once you go through this, once you know how one processor behaves, how it, why it behaves the way it is, and then how it is actually executing the instructions, how what is happening inside. Once you are aware of that, it really opens the way for knowing more and more about processor architecture. It not only makes you confident about processor architecture, it also makes you confident about what is happening underneath. So most of the time when we develop software, okay, computer science background, and we develop software, we always assume sometimes that okay, hardware is something which I don't have to worry about. Okay, that mindset is actually very wrong. For you to be a successful software engineer, you need to have a good hardware knowledge. In the sense, you may not be a good VLSI designer, but you should know processor architecture, how it behaves, why it behaves the way it is, so that you will be able to exploit the support provided by the architect. Similarly, if you are on a VLSI area and you are designing a, a big processor or a SoC, you may wonder that my area is hardware, so why should I bother about this word? Please remember, whatever we design as VLSI engineer, we want the software engineers to run their software on our hardware. So we need to take care of what they need, what their interests are, and what will make them run their software on our hardware efficiently with a minimal power with a high performance. So the hardware and software interaction is very essential to be a successful engineer or a system designer. Okay, the knowledge of both will actually help you out in terms of building a solution which meets the requirement of the software in the whatever software wants, it is there in the hardware, and then similarly software is tailored or written in such a way that the hardware features are exploited and they are used properly. So there should be a dialogue, a constant dialogue between these two parties for building a successful system. So my intent was to bring that kind of a flavor here. So I talked about a lot of architectural features, but I also gave you some why it is used a particular feature in the software world. So knowing both actually makes you a successful engineer, and at the end of the day, you feel that you know what is happening. The software when it is running on a particular hardware, you know what is happening in the hardware. So that really makes you comfortable, and especially when you are in debugging something, when there some problems and the crash is there, software is not working, then only you will see the handicap of not knowing what is happening in the hardware. Okay, and similarly, when you are a design engineer, when you are developing hardware and processor architecture and designing new processor architecture, you need to keep in mind what would be the requirement of the software designer. From the software perspective, what can be added to the solution so that it is easy for the software to run on them. So these two are kind of they have to hold hands together and make a journey. Then only the system that are built will be successful. And I hope I have made a small contribution towards this. And my intent was to make you aware as well as appreciate the both the sides of the world. Okay, and both are interesting in its own way. And knowing something about one side and knowing everything about another side will be always helpful for you to be a successful engineer, either you are on this side of the fence or other side of the fence. But I don't want to call it as a fence, but there should this particular border area should actually vanish, and the engineers should work together, understand each other's issues and problems and the requirements, so that end of the day, what we build is what is required for the users, and we can make the world better and safe. Because if you are an embedded software engineer, what you write or what you design, a software or a hardware doesn't matter. whatever you do might be very time critical, in the sense it can also be life threatening too. So it is very important that whatever we do a good job of it. Quality is very important, and whatever we do, either doesn't matter whether software or hardware, please make sure that you thoroughly test it and understand what is happening, so that you take care of all the conditions. It's not that the system that we build should go to the field or the customer's premise that to be tested. We have to anticipate all the worst case scenarios that could happen, and then build our solutions so that we really meet the requirements of the end market as well as the customers, and we make systems which are safer, and it consumes less power, so that it is economical in the sense, eco-friendly, as well as it is cost perspective, it is economical, and it meets the requirement of the people. Okay, and thank you very much for all your help and all your support during this time, and I hope it was useful, and I really enjoyed. And you can reach me anytime for any clarification or help. I really appreciate you, and I wish you all the best for your career in whichever path you take. And I also wish you, in case if you are interested in taking up software architecture as your research area, or to further go deeper into it, I really appreciate if this course has really created interest in you to take up software architecture as your uh, goal and the future career. Okay, thank you very much, and I wish you all the very best. And thank you. Bye bye.